Today, we'll be talking about mirrors. Images form where light from an object intersects. For flat mirrors, images appear to be behind the mirror. These images, because they're behind the mirror, are virtual, and they're not scaled or flipped. They have the same height and distance as the object. Concave mirrors are mirrors that are part of the inside of a sphere. When the object is outside of the focal point, the image is real in front of the mirror and inverted or flipped. If the object is behind the center of curvature r, then the image is smaller than the object. If the object is between the radius of curvature and the focal point, the image is enlarged. If the object is closer to the mirror than the focal point, the image is virtual behind the mirror, upright, and enlarged to appear bigger than the object. Convex mirrors are similar to concave mirrors, but have a different curve. The image of a convex mirror, in general, will be virtual, upright, and smaller than the object. The equations for distance of the objects, as well as the magnification of the objects, will work for both kinds of mirrors, as long as we follow a certain sign convention regarding distances and magnification. In general, we say that positive values mean that the object, image, or focal length will be in front of the mirror, and that a positive image height and magnification mean that the image will be upright. For negative values, we're referring to the object, image, and focal length being behind the mirror and the image being inverted. Similar to when we were working on resistor and capacitor combinations, this equation requires you to flip the fraction once you've found 1 over f. Don't forget to take the reciprocal to find f itself. In our first example, we have a concave mirror, and an object is placed 40 centimeters in front of it. The radius of curvature is 30 centimeters. Find the position of the image and its magnification. The first thing we'd like to find with this problem is the focal length, as we can use it in our equation for distance. The focal length is 1/2 of the radius of curvature, so we can divide the radius of curvature by 2 to find it as 15 centimeters. With our focal length now known, we can solve the equation for distances to find q, the distance of the image. Plugging in the focal length and the distance of the object, we find 1 over q to be 0.0417 centimeters inverted. We take the reciprocal of this to find that q is 24 centimeters. Now we can find the magnification. Plugging in the distance of the image and the object, we find that the magnification is negative 0.6. So the image is real because q is a positive number, and inverted because m is a negative number. The image will also be 60% of the size of the original object. In our second example, we have an object 75 centimeters in front of a convex mirror that has a focal length of negative 55 centimeters. We would like to know the properties of the image, namely, its distance from the mirror and its magnification. Using our equation for distances, we can plug in the focal length and the distance of the object to find that 1 over q is 0.032 centimeters inverted, and we can take the reciprocal to find that q is negative 31 centimeters. To solve for magnification, we plug in our values and find that our magnification is 0.41. Because q is negative, the image is virtual. It is also upright and smaller than the object because m is positive, but it is between 0 and 1.